short episode on Nebulae with Daniel T. Andreason on episode 337 of the Actual Astronomy Podcast. I'm Chris, and joining me is Shane. We are amateur astronomers who love looking up at the night sky, and this podcast is for everybody else who likes going out under the stars. So in our last show, we talked about an introduction to stars. We're doing a short series with Daniel. He's a listener who mentioned that maybe we could do a little bit more of the background on the astrophysics of stars. And as somebody who holds a PhD in astrophysics, we appreciate him helping out with the show. So welcome back, and thanks again, Daniel.
Yeah, no problem. Nice to be here.
So today we're going to talk about H2 regions, planetary nebulae, supernova remnants, and dark nebulae. H2 regions, they're one of those things that doesn't really roll off the tongue, but maybe we'll just start with Daniel giving us an explanation. Daniel, what are H2 regions, and what is an example of an H2 region that people might be familiar with?
Yeah, definitely. More or less everyone that listens to this podcast are probably familiar with H2 regions, even without knowing. And I remember I was told in my astronomy classes that the most photographed object outside the solar system from Earth is the Orion Nebula, which is an H2 region. And an H2 region is interstellar atomic hydrogen cloud of gas. So when I say it's interstellar, it just means that it's gas that are between the stars. And this hydrogen is ionized. That's where the two come in H2. If we have H1, we just have normal hydrogen atoms. But H2 is basically just a proton flying around, because hydrogen have one proton in the core and one electron around it. So when it's ionized, it's just a proton left over. And in these regions, we have a star formation, and usually something that happened very recently. And all the light from the newborn stars, they are the one ionizing all the gas around them. And that's why we can see things like the Orion Nebula, which is so beautiful, and we can see some of the stars in the cloud.
So it's the gas itself that's giving off a photon, and that's what makes it glow and be visible to us observers back here on Earth when we're looking at them, eh?
Exactly. And these regions, as the name suggests, they are mostly hydrogen, but that is the case for most things here in the universe, because hydrogen is the lightest element, and it was just the easiest thing to create during the Big Bang, at the beginning of the universe. And 75% of all the material in the universe that we know of is hydrogen, while just as around 24-25% is helium, the second lightest element. And then the rest, which we astronomers often just refer to as metals, even though they're not metals. So an astronomer only have three elements: hydrogen, helium, and metals.
I feel like there's a good joke there, but I won't chime in with that now.
Yeah, I remember one of my colleagues once had a T-shirt where he talked about chemicals in stars, and he had a T-shirt where it said "metal rocks," which I found quite amusing. But all this interesting part, which is just under 1%, probably is the backbone of life. I mean, we wouldn't be around here. If it was not for all these things that astronomers just lazily call metals. When we observe these H2 regions, we observe the emitted light coming from the stars being born there, and this is also the case for M2, which is so beautiful. And the reason why we also see other colors in M2, especially if you do some astrophotography, is because of all of these other elements that are also present in the nebula.
So with M42, have you been able to see any color in that in any of your own observing yet, Daniel? I'm kind of curious.
No, not yet. I'm still observing from my backyard, which is probably a Bortle 5 area. I didn't yet go to a dark side, which I guess is probably needed to be able to see some colors in that.
In my experience, just so that you know, you need a dark site, but it doesn't need to be the darkest site in the world. For example, my observing friend Mike, who's been on the show and we often refer to, he and I were able to see color in it just a 10-minute drive from my back door. Just, you know, there's not much behind my back door, but, you know, just on the outskirts of the city, really still in sight of the city lights, we were able to see some of the red tones. They're sort of like a very crimson, almost like a blood red tone in the Orion Nebula this past winter. So it's one of those things I think people just need to be open-minded to, that they can see color in the M42 Orion Nebula. So, but you know, really appreciate your explanation of that. This is really great. So maybe we'll move ahead to the planetary nebulae. I personally, I love planetary nebula. Not sure about you, Shane, but it's always really neat to go out and do some public observing at a place that's reasonably dark, and to show people that M57 smoke ring or the apple core shape of M27. Or if you get a good night, it's always fun to hunt down the helix on excellent nights. So what are planetary nebulae and how do they get their names?
Yes, so they're actually not planets. They have nothing to do with planets, other that they might have looked like planets in some of the first observations of them. So people just assume that this is not a pinpoint like a star. It looks more like a disk, like we see planets. So they were called planetary nebulas. And like so many other things in astronomy, names just tend to stick around. We don't bother changing things up. We already called it once. But these nebulas, they are formed near a red giant star's end of the life, which our sun will eventually end up in. And this is when the outer parts of a dying star is being expelled during these thermal pulses I explained a little bit about in the episode about stars. And in the center of these expanding shells from the star, we'll get this white dwarf where the sun eventually will become. And all the leftover these shells of the stars that are now surrounding the white dwarf is what we call a planetary nebula. And like the H2 regions that I just talked about, it's also an emission nebula, which means that it's the nebula itself that is shining. But here we see many other colors because there are heavier elements involved, because the heavier elements have been formed in the core of the star. We see, for example, oxygen. That's why we say that people should use an O3 filter, which is doubly ionized oxygen. O1 means that it's just normal oxygen, which is just an oxygen atom. And O3 means that 2 of the electrons have been stripped away. And probably one of the best known planetary nebulas, at least the one that I know the best, but not by observing, is the Ring Nebula M57, where the inner parts are O3, and the outer parts are more reddish, and they come from ionized hydrogen and nitrogen.
When you're observing, and you've probably observed M57, the Ring Nebula yourself, I would imagine.
Actually, I haven't started observing planetary nebulas yet. I only watched the Orion Nebula so far.
Okay.
Yeah.
So you're just getting into this. Well, that's going to be a real treat for you. The next time we hear from you, I'll be curious to hear about your observation, because it should be pretty high up. And as we get into July, when does it get dark there again for you?
Probably I will start observing again in August or September during the night.
Okay.
And that's when the clouds come back. So
that's when the clouds come back.
The life of an astronomer.
Yes, exactly. That's why I like solar observation now.
Well, I hope this next section is a real blast, but maybe I'll hand it over to Shane for this one to spare people the puns.
I can't believe you're giving up on that, Chris. Wow. So Daniel, I think the next topic here is supernova remnants. So I guess maybe just, what are they and why might they be kind of fascinating or get people's attention for observing purposes?
Yes, they are very fascinating objects, especially I think if we understand the process that created them and what is left there.
Mm-hmm.
So they are a little bit like planetary nebulas. It's also from a star that has died, but these are stars that are much more massive, above maybe 10 solar masses. So our sun will not end its life in a supernova and create a supernova remnant. But when a star is that massive and it's at the end of its life, it will die in the huge explosion called a supernova, and the leftover will be called a supernova remnant. That's basically it. And the remnant itself is the outer shelf of the dead star, and they can look in all different colors because there are many different kind of material being thrown out from the dead star. They're not necessarily as symmetrical as planetary nebulas. For example, the Ring Nebula, it really looks like a ring. It looks very symmetrical. But here we have something like the Crab Nebula that looks very different and not extremely symmetric like a normal ring nebula. And when a star ends its life in a supernova, it's usually because it's so massive that it's just the core is collapsing. It can no longer withstand the pressure from gravity, and it ends the life in a huge explosion. But there are also another kind of supernova, and this is when we have a white dwarf in a binary system, and is taking material from the other companion, which is maybe a red giant star. The material falls from the red giant star onto the white dwarf, and when it hits a limit in mass, there is an explosion, and we have a supernova. And these supernova are extremely useful to study other galaxies because they always explode at the same mass, so we know how luminous they should be. So it's a way of measuring distances in the universe, looking for these supernovas. Anyway, back on topic. There are a lot of heavy elements involved in a supernova. That's why they have all the different colors. And I think one neat thing about supernova is that all the heavy elements that are being thrown away and also being created during a Big Bang. A star can only make material up until iron, but during a supernova explosion, we can create even heavier elements like gold and uranium and so on. And I find it fascinating to think that the iron that is in our blood, the gold that is on our ring, or whatever it is, even what our telescopes are made of, are remnants of a dead star billions of years ago that polluted our molecular cloud when our solar system was formed. That is really fascinating, I think. And I already mentioned that there is a M1, the Crab Nebula, which is maybe one of the most famous one. But for me, from Denmark, the one I like the most is SN 1572, because it was discovered by Tycho Brahe, or Tycho Brahe, as you would say in English, which is a Danish astronomer. And he saw it in Cassiopeia and called it Stellar Nova, which means new star. He suddenly saw that there was something new there, which was in fact a supernova.
Interesting. Yeah, I'm just looking at this one right now. What is the magnitude?
I don't know that you'll find a magnitude for this one. For a long time, people thought it was not visually observable, but then with the larger, faster telescopes, people like Mel Bartels, who we had on the show a couple weeks ago, have discovered is that I think he and if I could be wrong, but I think he's one of the people that has observed this remnant. There's been a few others, but you need sort of a specialized telescope and really dark skies, but it is visually observable to see SN 1572. Strangely enough, a good finder chart for that is the Uranometria 1604, because they plotted it since that supernova was so well known in popular literature and still being discussed in astronomy circles in the early 1600s, when Johannes Bayer was creating that first really great star chart. He did plot it in several of the charts with Cassiopeia. So it is kind of neat to go back and look at that old chart and to actually see, and you can see the size, representing the stellar magnitude. It's about the size of the moon on the chart. It's just fantastic. There's a couple nova and supernova that are in there. I'm just looking out the window. We've got house wrens here, and they have no fear of us. One almost landed on my foot this morning, and I'm just watching my wife. She's sitting there, and they did just come and sit under her. So if you hear the birds going. Last nebulae that we're going to talk about are, these are some of the ones that I spent a lot of time observing, and they're the dark nebulae. So a lot of folks maybe haven't even bothered to look at these things before, but what are these dark nebulae, and how are they different from the other nebulae that you've talked to us about today?
Yeah, I think it's true that probably many didn't bother to look at them, maybe not on purpose. But if you are at dark side, you might actually accidentally see them towards the Milky Way, because you see these dark bands, which are dark nebulas. And what those are also a huge cloud of gas, but there are no stars nearby that ionize the gas. So it's just a huge clump of gas lying in the way of our line of sight. That's why they look dark, because we don't see anything at that region of the sky. But they are actually mostly just blocking the visible light, which can be annoying for us amateur astronomers, because we like to use our eyes. Some like to use the camera, but mostly we only work in the visible area of the spectrum. But it is possible to see through them with radio waves and infrared observations. And if you are looking at a dark cloud, I urge you to look at the edges of the dark clouds, because if there are some background stars, they might look very red near the edges. And this is because near the edges there is less of the cloud, so there's a bit of the light coming through the cloud, and this is mostly the red light, because all the blue light is absorbed by this dark nebula. So it seems like all the stars at the edges of a dark nebula are red, but this is just an optical illusion, because the dark nebulas are absorbing all the blue light. But they're very fascinating, and as I said, that these are everywhere in the Milky Way. So if you go to a dark side and look towards the Milky Way, you might actually be able to see some of these dark patches. And these dark nebulas, if they are being disturbed by external forces, this is where we can get star formation eventually.
I like that you point people towards the Milky Way, just even looking at it with the unaided eye, to start to see some of the dark nebulae, because even from a reasonably dark site, you can see those dark bands in the Milky Way, and those are dark nebulae. The most famous dark nebula, I always say, is sort of the most unfortunate dark nebula, which is Barnard 33, which was actually not discovered by Barnard, but discovered by Wilhelmina Fleming. And that is one of the toughest dark nebula to see. It's the Horsehead Nebula, just southwest of Zeta Orionis, and it's just such a tough one to see. It takes a very dark sight and usually a pretty good little telescope, or even a pretty good big telescope. But just going out, looking up, in particular, there's some really nice dark clouds like the northern coal sack, which is just up off of the star Deneb, just to the southeast of the North American nebula. So I like the fact that you pointed that out to people. Very nice. Thank you for that.
No problem.
So I think we're just about getting to the end of this episode. Any final thoughts to share with the listeners on Nebulae, Daniel?
No, I don't think so. I hope that I will be better at observing those, and I hope that others will too, because they're fascinating objects. And remember what you're looking at. I think that is the crucial part.
Very cool. Well, thanks again. And Shane, do you have any concluding remarks for this episode on the nebulae?
Maybe just one, and it would be a reference to an older episode. I don't know the number offhand, but nebulae is where your deep sky filters will come into play. So if you have some deep sky filters and you're, getting into some nebulae observations, this is where you'll pull out the O3s or the UHC filters, and sometimes those will help you to see more detail or even just see the nebulae in general. So if you're interested in that, go through the archive, and we definitely have 1 or 2 episodes just really talking about filter use and which ones are appropriate for different objects.
Well, thanks for that, Shane. Thanks for this episode, Daniel. We really appreciate it, and looking forward to the next 2 shorts. Thanks to the listeners for listening. You can always reach us with your show ideas, observations, or questions at actualastronomy@gmail.com.
Thank you, everyone, for listening, and we hope you enjoyed the show. If you are interested in more information, would like to contact us, or if you would like to support the podcast, check out our website, actualastronomy.com.